What does quantum mechanics really talk about? Many people have heard about some concepts of quantum mechanics, but few have a systematic understanding of it. Fragmented knowledge can lead to misconceptions, yet delving into the subject can seem daunting due to its foundational nature. So, why use the term quantum? What exactly is a quantum? Let's start by pondering how energy is transmitted. When you cool down a cup of hot water, it's because the hot water transfers its energy to the surrounding air molecules. Hot water molecules move vigorously, while air molecules move more gently. When a hot water molecule collides with an air molecule, it transfers its kinetic energy to the air molecule, reducing its motion. This gradual process causes the hot water to cool down. This is how energy is transferred. It's evident that energy transfer relies on interactions between substances, such as molecular collisions. In the process of cooling hot water, the temperature decreases from 80 degrees Celsius to 20 degrees Celsius. Temperature reduction is a continuous process, passing through any temperature value between 20 degrees Celsius and 80 degrees Celsius, like 50.654 degrees Celsius or 35.6521 degrees Celsius. This means that energy transfer in cooling water is a continuous change. While cooling water is a macroscopic example of energy transfer, in the microscopic world, energy transfer is not continuous but rather discontinuous. As I mentioned earlier, energy transfer relies on the exchange between particles. As we enter the microscopic world, these particles are likely to be the smallest units of matter, such as elementary particles. Elementary particles are the smallest particles, indivisible any further. In the micro world, all energy transfers essentially occur through the exchange of elementary particles, like photons. Photons can exist in quantities of 1, 2, or 3. There's no such thing as half or one-third of a photon. Thus, the energy carried by a single photon is the smallest unit in the process of energy transfer in the micro world. Suppose the energy carried by one photon is denoted as A, hv. In this case, energy transfer can only occur in multiples of A, such as 1A, 2A, 3A, etc., with no increments like 1.2A, 1.236A, or 2.58A. This means that energy transfer isn't continuous but rather discrete. This discrete unit of energy transfer is 1A, representing the smallest unit of energy. We attribute this phenomenon a new physics term, energy quantization. Therefore, quantum represents an indivisible fundamental unit. In the micro world, any concept that cannot be further subdivided can be called quantized. For instance, a photon is an indivisible elementary particle, thus also referred to as a light quantum. This non-continuous, indivisible quantum concept is prevalent in the micro world and forms its foundational phenomenon. Consequently, quantum mechanics is the theory that studies the micro world, thus earning its name. When we mention microscopic particles, many people mistakenly picture them as solid little spheres. In reality, the essence of microscopic particles is more like waves. To thoroughly grasp quantum mechanics, we must first assume that all particles are waves. These waves aren't like mechanical waves, such as water or sound waves. Microscopic particles present themselves in wave-like forms, permeating the entire universe. In theory, all waves can extend to the edge of the universe. While the spatial scale of a wave is infinitely vast, its energy often concentrates at a specific space scale, forming a wave packet. The more concentrated the wave packet, the more particle-like it appears. This duality between wave and particle is known as wave-particle duality. The uncertainty principle is a result of this wave-particle duality. Imagine microscopic particles as wave-like packets. The more concentrated the packet, the more it resembles a particle. The more spread out it is, the more it resembles a wave. These wave packets possess two distinct physical properties: position and momentum. Think of the position of the wave packet as its width and its momentum as its energy. If we want to measure the position, width, of this wave packet, particle, we need to strike it with photons. The information obtained from the photons allows us to determine the position of the wave packet. However, you'll notice that the measured position, width, range is relatively broad. For a more precise position measurement, higher energy photons are necessary, making the wave packet absorb more energy and become more concentrated, resulting in a narrower width that resembles a particle, and thus, a more accurate position measurement. Nevertheless, this increased concentration of the wave packet leads to a higher momentum due to the added energy, resulting in a significant deviation from the original momentum. Therefore, the momentum information obtained from this measurement is less accurate. To measure the momentum accurately, lower energy photons are required, which leads to a wider wave packet and hence, less accurate position measurement. Werner Heisenberg suggested that a particle's wave packet's position and momentum information cannot be precisely measured simultaneously. The more accurately the position is measured, the less accurate the momentum becomes, and vice versa. He proposed that this phenomenon primarily arises from the particles used by measuring instruments. However, contemporary quantum theory contends that Heisenberg's interpretation is not entirely accurate. While measurement instruments do indeed interfere with the measured objects, the fundamental reason lies in the intrinsic nature of particles. Yet, Heisenberg's term, uncertainty principle, can be misleading, as it implies a limitation due to the measuring technology. Today, the term has been updated to the principle of uncertainty. Another prevalent characteristic of microscopic particles is the principle of superposition. This principle's mathematical interpretation can be complex and dull. Superposition, or quantum superposition, means that a particle, like an electron's spin, can simultaneously be up and down. This perplexing phenomenon also bewildered Schrödinger. To simplify the concept of quantum superposition, let's extend it to the macroscopic world, the scenario of Schrödinger's famous dead and alive cat. If you imagine microscopic particles as waves, understanding quantum superposition becomes easier. This wave permeates the entire universe but isn't evenly distributed. There's a wave packet on this wave, and wherever the wave packet is located, we say the particle is there. The challenge is that in theory, this wave packet could appear at any position on this wave. As the wave spreads throughout space, we say the particle could be anywhere. Measurement, however, causes the collapse of the superposition state. When you measure a particle's position, the wave packet collapses due to the interference caused by the measuring particles. As observers, if we don't measure this wave packet, particle, it remains intertwined with the wave. This leads to the particle's position being a superposition of various locations, hence appearing to be here and there simultaneously. This is the essence of superposition. Quantum entanglement is when two entangled particles are, in fact, the same wave, composite system. The act of measurement results in the collapse of this wave into two wave packets, particles, which were originally in a shared superposition state, and measurement causes this superposition state to vanish, giving rise to two definite wave packets, eigenstates. But as observers, we seem to perceive these two particles, wave packets, acting simultaneously across space, demonstrating the phenomenon of quantum entanglement. Essentially, entangled particles are, at their core, the same particle. Thus, measuring one particle is, in fact, measuring the other, making quantum entanglement an instantaneous occurrence. Yet, this entanglement doesn't involve any actual material movement, hence it cannot convey information or energy. Why then don't we observe quantum superposition in the macroscopic world? In reality, the laws of this universe don't differentiate between the macroscopic and microscopic realms. Both are fundamentally governed by phenomena of the micro world, and quantum superposition is actually the most universal and normal phenomenon in the cosmos. Our inability to grasp quantum superposition arises from living in a macro world where superposition has already collapsed. Newtonian mechanics, derived from macro world observations, has become a preconceived notion, leading us to believe that non-superposition states are normal, while superposition seems abnormal. The disappearance of superposition states in the macro world is due to the large size of macroscopic matter. The constant bombardment of photons present everywhere in the universe causes interference with macroscopic matter. This interference, in essence, parallels the collapse effect of measurement, thus causing superposition states in the macro world to collapse and exhibit definite states. The most direct proof of this is found in the superposition of air molecules. This demonstrates that even substances much larger than atoms, as long as they are undisturbed by other particles, akin to the collapse effect of measurement, can still exhibit superposition. However, in practice, substances a bit larger than molecules will inevitably be influenced by other particles, causing the superposition state to be disrupted and collapse. Thus, we now understand that a photon is a wave packet, and many of its properties are in a superposition state. If you were to replicate this photon state, you would need to split the photon into two. However, photons are indivisible, preventing this method. The other approach is to measure the photon's information and then recreate a similar photon based on this information. But, due to the collapse effect of measurement, the original superposition state of the photon would be lost. Hence, you can never obtain the original superposition state of the photon, and this inability to clone a single photon is a fundamental property. Traditional electromagnetic wave communication involves transmitting a multitude of photons with varying frequencies, where photon frequency corresponds to zeros and ones. Eavesdroppers can intercept a few photons during transmission and decode the content based on their frequencies. In contrast, quantum communication employs the principle that single photons cannot be cloned for secure quantum key distribution, promising absolute security. Eavesdroppers trying to intercept quantum communication must either intercept photons or measure them. If they intercept, they'll be detected as the single photon will be missing, indicating a compromised communication process. If they choose to measure, the collapse effect of measurement will be triggered, again leading to detection. In quantum communication, any eavesdropping attempt will certainly be detected, leading both communicating parties to abort the current session. Although information interception isn't alarming, the problem lies in interceptors gaining access to the content. Quantum communication's primary achievement is verifying whether the communication process was compromised, rather than preventing eavesdropping. Even if an eavesdropper continuously listens, they can't extract useful information. Hence, quantum communication security is absolute. This is the core idea of quantum communication today.